Alright, this is going to be lecture 1 over chapter 1 for electrical components. Alright, so chapter 1 we're going to cover quantities and units. So we're going to go over scientific and engineering notation. You're probably familiar with scientific notation, but you're not familiar with engineering notation. We're going to go over different units, our metric, our SI stuff, different quantities of how we measure electrical units, so resistance, ohms, and voltage and those sort of things. We're going to talk a little bit about electrical safety at the end. So first, scientific and engineering notation. Why do we use them? Okay, so with scientific notation, we can take a really large number and truncate it so it's a little easier to use. So take for instance an earthquake. You see that it's like a 4.5 on the Richter scale. Well, that number is actually really big in magnitude. And it's actually a number that we take and make much smaller and put it into scientific notation, so it makes sense. Same with decibel gain. So when you're turning up the volume on your stereo or things like that, we're going to use, scientific or engineering notation there. Engineering notation for us is we have set quantities for like current, resistance, capacitance, inductance, and things like that. So we want to quantify them using SI prefixes. So we have to write things in engineering notation so that it's easier for us to have a universal set of units as we go across the globe. What we use here in America needs to be the same as what they use in Europe, same as in Asia and India and all those other countries around the world. We want to be on common ground. So every country in the world uses the same engineering notation. So but for the most part, it's a convenient way of representing either really large numbers, like I talked about with earthquake and Richter scale, and very small numbers. When we start talking into micro or things like that, nanite technology, very small sort of things that come into play. Okay, so they both have powers and have a base and an exponent. So this is how they're similar. All right. Decimal system, so we're going to take times 10 to some exponent. It's going to be different between scientific and engineering notation. Alright, but if we take a look back just for our review, alright, our regular decimal system that you and I use every day, is a base 10 system. So our numbers that we count through, 0 to 9, that's 10 digits. Alright, so that's why it's our decimal system. And that's why it's a base 10, because 0 to 9 is 10 digits, and then we just increase the number in front. So we go 0 to 9, then we're going to go 1 0, 1 1, 1 2, 1 3, right up to 1 9, which is 19 to us, and then we increment again. So that's why it's base 10. Binary, base 2. Most of you guys that took my digital electronics class, right, we covered a lot of binary systems. It's base 2. Why? Because there's only two components. There is a 0 or a 1. That's it. That's the base, and we increment zeros and ones to represent other numbers. The octal system, right, it's a base 8. Base 8. So kind of like the decimal system is base 10, octal system is base 8. What does that mean? We only use 8 digits. So we use 0, 1, 2, 3, 4, 5, 6, 7, and then we repeat over. So in octal, there are no digits 8 and 9, if that makes sense. So we'll go 0, 1, 2, 3, 4, 5, 6, 7, and then increment again, 1, 0, 1, 1, 1, 2, 1, all the way up to 1, 7, and then start over to 0, and so on and so forth. So we're skipping the digit 8 and 9 because it's a base 8 system. Hexadecimal is a base 16, all right? A lot of the stuff that we use in the computers, we take a binary coded decimal and do those sort of things, and we truncate it down. Hexadecimal is very important. It's a base 16. Are we going to hit these heavy? No. We're going to talk about those a little bit more in the PLC class, the octal and the hex. We're just going to brush on them in this class. We aren't really going to touch on binary in this class either. Everything we're going to do is decimal system. Our scientific and engineering notation are in decimal system, and that's how we're going to do it. But hexadecimal, all right, it's base 16. It's 0 through 9, okay, 0 through 9, and then we don't have 10, we start with letters, all right? So 10 is essentially A, 11 is B, 12 is C, 13 is D, 14 is Z, 15 is F. So 0 to 15, digit-wise decimal for us, all right, but it's really 0 to 9 and then A through F. That represents, okay, 15 different digits, and we use a combination of numbers and letters to get into that hexadecimal system. All right, but we'll cover that more in another class. I don't expect you to remember everything about binary, octal, and hex. And those of you that took digital electronics with me, right, we did cover octal and hexadecimal already. All right, but just looking at your basic number system that you started with in elementary school. So when we first learned math back in first grade or things like that, we learned about the ones, the tens, the hundreds. All right, but this is how we represent them as a decimal. 10 to the 0 is the ones, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, tens, those sort of things. 10 to the first. 10 squared is our hundreds, right? So on and so forth. We can see all the way up to trillions. I'm not going to review the basic math piece for you guys, but just know that you've been using the decimal system your whole life, essentially. Your computers use the hexadecimal and binary system and octal, all in a combination of type scenarios. So we can take a binary number like 0, 1, 0 and write it in, that's kind of our octal truncation. Or we can take the number 1010. It's a binary number, but it's also can be represented as a hexadecimal. So same kind of concept there, or into hex, sorry, or binary coded decimal. That's really why I wanted to go with that. So that's how we take a binary coded decimal, but it's really kind of like a hexadecimal in that scenario. But moving forward here, scientific notation. So these are the rules for scientific notation. So I would make sure that I have these, that you have these in your notes. All right, scientific notation has one digit to the left of the decimal place. So it has to be a 1, 2, 3, 4, 5, 6, 7, 8, or 9. You cannot write like 10.25. That is not in scientific notation because that's 2 digits in front of the decimal. That's not allowed for scientific notation. Only the digits 1, 2, 3, 4, 5, 6, 7, 8, 9 can appear before the decimal point. Okay, and then we're going to write times 10, and then it's going to be to some exponent. All right, the exponent can be either positive or negative. Positive meaning the number is greater than 1, negative meaning the number is less than 1. Not meaning the number is positive or negative. It means the number is either greater than 1 if the exponent is positive. It means the number is less than 1 if the exponent is negative. All right, so let's take this number here. We have 47 million. All right, so if we look at this number as is, the decimal is all the way to the right of that last 0. So we have to move the decimal place 1, 2, 3, 4, 5, 6, 7 places to the left. Not because of the number 7 in 47, but because that 4 will be our single digit to the left of the decimal place. So we're going to represent this as 4.7 times 10 to the 7th because we moved the decimal 7 places. All right, so that's really what it is. We start with the decimal all the way to the right because it's not written down, and we're going to move our decimal 7 places to the left. We have to move it 7 places because we're going to get it so that we have a single digit to the left of the decimal place. All right, right now we have 8 digits to the left of the decimal place, and we cannot do that with scientific notation. All right, this is a number that is less than 1. In my mind, automatically, I'm thinking, all right, negative exponent. This time I see the decimal place, and I have to move the decimal place a certain number of places so that there is, what? 1 digit in front of the decimals. For us to do that, if I point at the decimal and I move it 1, 2, 3, 4 places, okay, just past that first 2, I will get 2.2. Okay, 2.2, and then I have to keep track of how many places I moved it. I moved it 4 to get there, and since I moved it to the right, and this number is less than 1, it's going to be times 10 to the negative 4th. Okay, so every single time we're writing something in scientific or engineering notation, we're going to be writing that times 10, all right, to some exponent. The exponent is the number of decimal places that we moved. If we moved the decimal to the left, the exponent will be positive. If we move the decimal place to the right, the exponent will be negative. How do we know how many places to move the decimal point? We move it until there is only one digit in front of the decimal place. So that's why in the first one we moved it to where the 4 was, and the second one between the two 2's, so that only one 2 resides before the decimal. Engineering notation. Engineering notation, slightly different than scientific notation. Okay, scientific notation, we were limited to the digits 1 through 9 before the decimal place. Engineering notation can have up to 3 digits before the decimal place. So anything from 1 up to 999 can be to the left of the decimal place. The most important part that everyone forgets about engineering notation, your exponent has to be in multiples of 3. So when you're doing engineering notation, no matter what, you cannot move the decimal place one decimal at a time. You have to move it in chunks of 3. Okay? If you can't move it in 3, then you can't move it. The rule is you can only move the decimal in groups of 3, not by 1 like we did with scientific notation. Alright, so let's take a look at that very first one that we did before. Alright, we put this one in scientific notation, but let's put it in engineering notation. It's going to be a little bit different. We have 47 million again. The decimal's all the way to the right, so we're going to move that decimal, remember, in groups of 3 now. So 1, 2, 3, 1, 2, 3. Now 47. That's acceptable because it's between 1 and 999 is what's going to be to the left of the decimal place. Then it's going to be times 10 to the what? 6th. Okay? So in this case, it's 47 times 10 to the 6th. So with engineering notation, the exponents have to be a multiple of 3. So we can have an exponent of 0, 3, 6, 9, 12, 15, 18, 21, 24, so on and so forth that direction. We can also go 0, -3, -6, -9, -12, -15, -18, and multiples of 3 that way. So the exponent will always be in multiples of 3. Very, very, very important. Okay? Next, we're going to take the same one we did in scientific notation. So we have 0.00022, and I'm going to move it in chunks of 3. So I'm going to move that decimal 3 chunks to the right. I have 0.22. That's not acceptable. It has to be between 1 and 999. So I have to move it 3 more places. If there's no digit out there, you can keep going to the right and adding zeros. So I can write a 0 to the right of that too. So I can move the decimal 1, 2, 3, 4, 5, 6 places now. Okay, remember I'm in chunks of 3, and I can add zeros till the cows come home, all the way to the right of a number, and it does not change that number when it is less than 1. Okay, so when we do this, we're going to end up with 220 times 10 to the -6. Remember, minus because we're moving the decimal to the right, 6 because we had to move it 6 places to the right. Okay, we're going to find out that 10 to the 6th means something. 10 to the -6 actually means something when we're going to get into our SI prefixes soon. So it's very, very important that we do our engineering notation correctly. We're not going to harp on scientific notation in this class. I'm going to ask you a couple test questions on it, and then we'll be done. We will be living in engineering notation, all right, the rest of your mechatronics courses with me. And anything, if you go beyond mechatronics and you go into engineering, all right, whether electrical, mechanical, chemical, industrial, all of those, you're going to use the same set of engineering notation. All right, so let's do one. I'll give you guys a second to do this one. All right, so pause the video and see if you can do it right. Kind of separated out things. Okay, so go ahead and pause it, try it, and then we're going to pick up here. So let's look at this number here. All right, it's less than 1. I automatically know I'm going to have a negative exponent, and we're going to do scientific notation first. Remember, to get these straight. So scientific notation, only 1 digit in front of the decimal. So I have to move this 1, 2, 3, 4, 5 places to the right. All right, those 3 zeros, the 0, and then the 2. So I'm going to get 2.7 in this scenario, okay? And then it's times 10 to the negative 5th. Hopefully this is ringing some bells. You guys should have done this in science class some point in your life. All right, now let's put this same exact number in engineering notation. Now we have to move it in chunks of 3. So remember, engineering notation, chunks of 3. I guess if it helps, the word engineering has 3 E's in it, so know that you got to move the decimal 3 places each time. So if we do it this time, why don't you pause the video, see if you can write it out correctly on your own, and then when unpause it, we'll be going over it. So we're moving it 3 places to the right, so so we'll move it 1, 2, 3, so that'll give us 0.027, which doesn't work, right? We have to be between 1 and 999. So we got to move it 3 more to the right. So we're going to get 27 times 10 to the minus 6. Remember, it's minus because it's less than 1. And we're moving the decimal to the right, so we're going to have a negative exponent. Okay? So let's do this one. Why don't you pause the video, see if you can put this in scientific notation. This one's a little easier. We only got to move the decimal 1 place to the right. Alright, so this is 6.05, alright, times 10 to the minus 1. Remember, it's still the number's still less than 1, so we're going to have that negative exponent. Alright, why don't you pause it and try and put it into engineering notation real quick. So remember, in engineering notation, we can't move it 1 place, we have to move it at least 3. So we're going to move it 3 to the right, and we're going to get 605 times 10 to the minus 3rd. Okay? We had to move it 3 places. The number is still less than 1, so we have a negative exponent. So that's where we are with engineering notation. All right, we're going to do a few more examples kind of as we roll through this. Your calculator can help you with that times 10. So the EE key, regardless of if you have an old school generic calculator like this, or you have the fancy TI-89s, TI-84s, TI-83s, any of those, all your calculators, and I believe even your phone, if you turn your phone, when you have your calculator on, you turn it sideways, I think it has the EE key. Alright, the EE replaces the times 10. So if I wanted to write like 4 times 10 to the 6th, I could write 4EE6. Alright, and you just hit the EE button on your calculator when you do that. On the generic, old school ones, it's going to be right there, but that EE replaces the times 10. So once again, if I had 4 times 10 to the 6th, I could just write 4, hit the EE button, 6. Or in my calculator, I could write, 4 times 10 to the power of 6 as well. Either way, whatever is comfortable for you. Alright, graphic calculators, same way. You just got to kind of look on your calculator faceplate, see where it is, and see how to input it. Alright. This is where we're going with engineering notation. We're going to use the SI units. You guys probably just know them as metric system, right? Over here we use imperial, so we have foot, pound, and that sort of thing, instead of using, meters and kilograms and that sort of thing. But we do use SI for all of our engineering units, okay? So as we go through this, these are all the ones that we are going to use in this class. So our fundamental units, we're going to use all of these at one point or another through all the mechatronics courses. Alright, but the SI fundamental unit for length, alright, mass, time, current, temperature, luminosity, that's how much light gives off. If you have to know like the electrical code and you have the overhead lights, if you look up in our classroom, look at the overhead lights. Alright, each one of those has a certain amount of luminosity, and so when you're designing buildings, school classrooms have to have a certain amount of luminosity. Office buildings have to have a certain amount of luminosity. Alright, so you have to make sure that when you're designing something, there are a certain number of lights in that area. Alright, amount of a substance we have. So some of these, okay, you should know. Length, meter, the symbol for meter is a lowercase m. When we start talking about mass, we're going to talk about kilograms. Okay, kilograms. Time is always going to be in seconds for us. Current is an ampere. We're going to use the symbol A for amps. Temperature, Kelvin. We're going to use a capital K. We're going to hit a lot more on temperature and fluid power and things like that. We're going to use Kelvin, Rankine, Celsius, Fahrenheit, all those goodies, okay? Luminous intensity, okay, that's called a candela. We use a CD. We aren't going to do too much with that. Those of you that go on to be electrical designers or things like that, you're going to deal with that more. All right, moles, molecules, those sort of things, chemistry, amount of a substance there, okay? Stuff that we're going to focus on more in this class: current, charge, voltage, resistance, and power. We're going to be using this a lot throughout the entire semester. So current, all right, is an ampere, and we use it with an A, all right? We don't use C because C is speed of light, all right? And we're going to use I for current, all right, in the engineering world, and then we use J for complex numbers and things like that. But I don't want to fill you with too much there, all right? The unit of charge is a coulomb, represented with a C. Voltage is a volt, represented with a V. Resistance is in ohms, represented with a Greek capital omega. Power is in watts with a capital W. Okay? So make sure you can always pause the video. I'm going to always keep moving forward. But make sure that you have these in your notes because you will have a quiz on the lecture notes at the end. So make sure you're taking good notes, writing these down. Alright, here are the engineering metric prefixes that we are going to use. So I suggest making sure that you are putting these in your notes. Okay, these are called the large prefixes. So these are the numbers that we're talking about when we are greater than 1. Greater than 1. Okay, so P is peta. That's 10 to the 15th. Very, very large number. We aren't quite there yet with hard drives, but you will recognize T. All right, so if you have a terabit hard drive on your computer or things like that, that's 10 to the 12th. Very large number. Okay, giga, that's 10 to the 9th. Most of the, our little thumb drives are gigabytes, or you have 16 gigabytes of RAM, all right, things like that on your computer. Those are common terms, and that's kind of where they come from, in the engineering notation. Okay, capital M is mega. Do not confuse that with lowercase m. Mega is 10 to the 6th. Kilo, 10 to the 3rd. If you look at all of those on the right-hand side, 10 to the 15th, 10 to the 12th, 10 to the 9th, 10 to the 6th, 10 to the 3rd, those are all multiples of 3. This is all going to tie back to engineering notation. All right? So we might have a 25 kilo ohm resistor. Okay? So we're going to use things like that. That's why it's important, because we're going to have to go into engineering notation and then go from engineering notation to SI notation. All the small numbers, so make sure you're pausing the video and writing all these down. Alright, and we're going to go, close to 1 and then get really small. So a lowercase m is milli, that's 10 to the minus 3. The next we have is the Greek letter mu, and it will be micro, that's 10 to the minus 6. So a lot of the current we're going to talk about is in milliamps or microamps. If you start looking at like your block for your phone charger, all right, and you can kind of see if it says, you're not charging that thing with amps, you're using milliamps and things like that. Much safer currents. Okay, nano is 10 to the minus 9th, right? You've heard of nanotechnology and things like that in movies. Very, very small, right? We've got Ant-Man and that sort of stuff, right? Picofarads. We're going to talk about that for capacitance and things like that. So 10 to the minus 12th. And femto, we don't use a lot of stuff in femto. Femto is 10 to the minus 15th. So those are all these small engineering prefixes. So we're going to go through and kind of use those here in a little bit. But we need to be able to convert back and forth between a larger unit of measure and a smaller unit of measure. And we got to know which way we're moving the decimal. So in this case, we're going to go from larger to small. We're going to move the decimal to the right. Okay, so what does that mean? I have 0.47 mega ohms and I need to move to kilo ohms. Let's think about that real quick. Mega is what? 10 to the 6th. Kilos 10 to the 3rd, right? You can reference the chart we did on the last slide. So how far apart are those exponent-wise, right? Mega's 10 to the 6th. kilos 10 to the third, we should know that those are 3 apart. So we only have to move the decimal 3 places to get to kiloohms from mega ohms. Okay, so when we do that, megas 10 to the 6, kilos 10 to the third. So when we do that, I take that decimal and move it 3 places to the right, and I get 470 kiloohms. So we're going mega, which is bigger than kilo. Alright, and they're 3 apart. So since we're going bigger to smaller, we move the decimal to the right 3 places. Bigger to smaller, move the decimal to the right 3 places. Let's do some practice here. These are what? All bigger to smaller. So if we remember, what's that omega? That's ohms. So we're talking about unit of resistance here. So make sure these are all samples in your notes here that we're going to be able to have here. So we got 20 mega ohms is equal to what? 20,000 kiloohms. I had to move the decimal to the right 3 places. Now to go from kiloohms to ohms, that decimal is 3 places as well. So I got to go 3 more places to the right. Okay, so 20 mega ohms is the same as 20,000 kiloohms, which is the same as what? 20 million ohms. Alright, let's do the next one. We got 3 mega ohms, which is 3,000 kiloohms, which is 3 million ohms of resistance. So why don't you try this one real quick, pause the video, give it a shot. Go from 0.5 mega to kiloohms. Alright, go ahead and pause, do it, and we'll convert here. So we're going to move it what? To the right 3 places. So 1, 2, 3, adding zeros as we go. So 0.5 mega ohms is 500 kiloohms. And then we replace that K with 3 more zeros to get 500,000 ohms. Do you see how each prefix is 3 places, right? The 0.5 mega, we replaced the mega and went to kilo because we moved the decimal 3 places to the right and got 500. We replaced the K with 3 zeros. Alright, 10 to the third is 1,000, which is 3 zeros. So that's why it's 500,000 ohms now. So we can replace the engineering notation with all the prefixes that we just learned. Alright, so we have 0.07 mega ohms. You should know by now that that's 70 kiloohms. 70 kiloohms is really 70,000 ohms. I think you guys are getting the gist. Hey, and you can pause in between all of these so that you make sure that you're really getting them down pat. We got 0.001 mega ohm, which should be what? 1 kilo ohm, and 1 kilo ohm is 1,000 ohms. That's the important one to know, okay? Kind of as we go through all this. Alright, we're going to go the other way now. We're going to convert from a smaller unit to a larger unit. Now we're going to move the decimal to the left. Alright, a larger unit means the number has to be smaller. Okay, because we're talking less than 1. So we have 10,000 picofarads, and we need to convert that to microfarads. First of all, I'm going to ask you, and when you do your homework problems and you do the quiz and things like that after the lecture, alright, ask yourself, hey, what's pico? 10 to the what? Right? Pico's 10 to the 12th. Micro's what? 10 to the 6th. How far apart is 10 to the 12th and 10 to the 6th? 6 decimal places. So make sure that you understand how far you have to move them first. Alright, so picofarad, that's the lowercase p with the f. We're talking capacitance. That's why I'm saying picofarad, that pico f. Farad is a unit of capacitance. We're going to get into that. Alright, microfarad, 10 to the minus 6th. So what should we be doing? We got 10,000 picofarads, which is a larger unit than microfarads. We have to move that 6 places to the right. So 1, 2, 3, 4, 5, 6, so it's 0.01 microfarads. Is that acceptable engineering notation? No. But what's the point of this? Is being able to convert between a larger unit and smaller unit. So, okay, sometimes with capacitance we're going to see units like 0.01 microfarads, okay, or things like that, because they actually print these tags on the capacitors and things like them themselves. So it's easier for them to write 0.01 microfarads than to fit in 10,000 picofarads. They both mean the same thing. It's the same amount of capacitance, all right? But no, pico's smaller, right? And then micro is larger, okay? So in this case, we're going smaller to larger unit. All right, let's do some more examples here. We have 20,000 picofarads. We're going to go to nanofarads. We're going to go to microfarads. We're going to go to millifarads, and then we're going to go to farads. Hopefully I got enough room on here, all right, when we do all this. But notice on the micro, all right, I wrote a U. Instead I didn't really pull in the symbol from PowerPoint for the mu. But you can either write a mu or lowercase u. I will understand what you're writing. Don't write a M for micro because M is for milli. All right. So pico to nano is what? 3 units. So we got to move the decimal place 3 places. All right. So that 20,000 now becomes 20 nanofarads, which is 0.02 microfarads. We had to move it 3 more places, right? And then we had to move it, what, 3 more places to get it into millifarads. And then we had to move it, what, even 3 more places to get into farads. So that's a really, really, really small number. All right? So although that's, you know, a decent amount of capacitance, and that will shock you very, very good, it is a very, very small number. All right? It's 20,000 picofarads versus, and this is kind of, we write it, we would most likely probably write this as 20 nanofarads on the side of the capacitor. It's the cleanest looking one. You might see it as 0.02 microfarads. Those are the 2 cleanest. Do you see why it makes sense we don't use the one on the right and say like 0.000000002F? Okay? It's a lot to say. When I can reel that off, instead of reeling off that whole number, I can just say, hey, it's a 20 nanofarad capacitor. That's the whole reason we use these conversions. All right, so let's look at the next one. We got 3,000 picofarads. Pico to nano, we got to move it 3 places. All right, nano to micro is 3 places. All right, and this is all off the table we wrote down on the prefixes before, right? And we went milli, micro, nano, pico, femto, all those. Okay. Move it 3 more places. Move it 3 more places. I think you guys get the gist of kind of what we're doing here. All right, we got 500 picofarad, that's 0.5 nano, 0.005 micro, even more zeros. Each time, what are we doing? We're adding 3 more zeros because we're moving it in chunks of 3. So 10 picofarads is 0.01 nanofarads, 0.00001 microfarads. All right, you get lost in the zeros, especially on this last one. There's a whole plethora of zeros there, okay? Much easier for us to say, hey, this is 10 picofarads. All right, but the point is we're going from a small unit in picofarads to a large unit in farads. All right, and pico and farads are what? 12 apart. So if I asked you to go from 10 picofarads to farads, you'd have the number on the left you start with, and the number all the way on the right is what you'd end up with. Those two, same amount of capacitance, they are equivalent. All right, so let's add and subtract these. Okay, it's going to be important when we start adding resistors, but you need to make sure that you're either all in SI prefix or all in their base unit. Notice one's in ohms and one's in kilo ohms. So always, always, always be in the same units. So let's take that 22 kilo ohms and write it as 22,000. So now we can do 10,000 plus 22,000. Do not do 10,000 plus 22 and get 10,022. You are incorrect, because it's 10,000 plus 22 kilo ohms is 22,000, right? Remember, because kilo is 10 to the third, meaning that K represents 3 zeros there after that number. So that's why it's 10,000 plus 22,000 is 32,000, all right? Or I could have taken that first number, 10,000, and written it as 10K, and I could have done 10K plus 22K and gotten 32 kilo ohms. Both of those numbers mean the same exact thing, 32,000 ohms of resistance. All right, let's do that with a smaller number. We have 200 microamps, which is, we're going to add it to 1 milliamp. So we can either take that micro and write it as milli, or take that milli and write it as micro. So let's do this first. We're going to take that milli and write it as micro. So we got 200 microamps plus 1,000 microamps and get 1,200 microamps. And then we'll use the other method. We'll take that 200 and write it in terms of milliamps. So it's 0.200 milliamps plus 1 milliamp. So we get 1.2 milliamps, and that's equivalent to 1200 microamps. But for us, right, 1.2 milliamps is easier to say and much more efficient for us to use. All right, let's complete this table here. So what I want you to do in your notes is pause the video. All right, wait, I'll give you instructions. All right, so we're gonna pause the video and write down this table as you see it, and then we're gonna fill it in. If you think you can fill it in as you go right ahead. But write this out and then make sure that this is in your notes. It's gonna be very important. So we have 50,000 volts. We want to write that in engineering notation. Remember, engineering notation, the first digit has to be between 1 and 999, followed by 10 times 10 to the some multiple of 3. So in this case, you should have gotten 50. Okay, and we move the decimal 3 places to the left, so we get 50. Those 3 zeros, okay, are times 10 to the third. So we had to move the decimal place 3 places. Now, scientific notation. Remember, can scientific notation and engineering notation be the same number? In some cases, yes, as long as that scientific number has a power that is a multiple of 3. In this case, is it going to have that? No. Remember, scientific notation, the digit before the decimal has to be between a 1 and a 9. So we have to move the decimal 4 places to get to scientific notation. So this is going to be 5 times 10 to the 4th. All right. Remember, the SI only applies to the engineering notation. All right. There's 2 parts to this SI. One's the unit is volts. The other is we have to replace that times 10 to the third. If you remember, 10 to the third is what? Kilo. Okay. So we're going to replace that times 10 to the 3, and we're going to replace it with a K. So you should write it as 50 kilovolts. And it does matter. It does have to be a lowercase. All right, the next we have 25 million ohms. In engineering notation, 25 is acceptable. We have to move that decimal place 6 places, so we should get 25 times 10 to the 6th. All right, engineering notation, the digit has to be between 1 and 9, so we have to move the decimal 7 places, so we're going to get 2.5 times 10 to the 7th. The SI has to do with the engineering notation. We have to replace that times 10 to the 6th with what? Mega. Alright, so this becomes 25 mega ohms. Capital M, and the symbol for ohms is the Greek capital Omega. So you should be starting to learn these a little bit now. Alright, next we have engineering notation for 0.003 watts. Alright, engineering notation, we're going to have to move that how many places? 3 places to the right, so we're going to get 3 times 10 to the negative 3. How about scientific notation? We also have to move it 3 places to the right and get 3 times 10 to the negative 3. This is a scenario where engineering notation and scientific notation can be the same. Now, SI, okay, you got to reference back to your table. What's 10 to the negative 3? Okay, it should be milli. So lowercase m. So we're going to rewrite this as 3 milliwatts. Okay, the W is the symbol for watts, so lowercase m. So make sure that we're not confusing those, right? The one before had a mega, a capital M, and a lowercase m. That's a huge difference in your numbers, so you really got to be careful there. All right, let's do this last one here. We got 0.000050 amps. Well, we got to group that in chunks of 3. So we got to go 1, 2, 3. And then we got to do another 1, 2, 3 because that number is not between 1 and 999 yet. So we have to move it 6 places. All right, so when we write it 6 places, we're going to get 50 times 10 to the minus 6. Okay, 50 times 10 to the minus 6. All right, scientific notation. Okay, we don't have to move it 6 places. We have to move it 5 because that digit has to be between 1 and 9. So we're going to get 5 times 10 to the minus 5th. The metric units apply to the engineering notation, so we have to replace the times 10 to the minus 6 piece with its SI prefix, which is what? Micro. All right, so 50 micro, and then amps is used for an A. Okay, good. Hopefully we're starting to get the gist of this one. All right, so if you want to you can pause the video, write this down, and I'd like you to, practice doing this one on your own. I'm not going to walk you through each one like I did on the last example. This will be on your test, all right? Your major quiz, and you'll probably have to do something like this on your lecture quiz as well, and you will be doing a lot of this on your homework. So I would take the time, pause the video, fill this out, and then check yourself. I'm going to populate the solutions for you here so you can take a look and see if you did them all correctly. But like I said, I'm not going to walk through this one on you, but go ahead and check yourself. You should be gaining an understanding and getting most of these down. Alright, so let's talk about error, accuracy, and precision. Alright, uncertainty is part of all measurements. So accuracy, we have to really understand that. It's an indication of the range of error in a measurement. That's what accuracy is. It's a range of error. Alright, so we got the bullseye target here. Okay, the error is how far we are from what we want to be at. Alright, so if we hit the bullseye, or how far away we are from the bullseye, that's our error. Alright, how far we are away from where we intended to aim. Okay, precision is a measure of repeatability. Alright, so this is being precise isn't always a good thing. Alright, here's why. Alright, if we look at the second target, right, those arrows are all very precise. Very, very precise. But they are all very precisely what? Wrong. We're not even close to the bullseye. Okay? Now, maybe you're playing darts and you're going for 20, right? You just got a boatload of points and you threw more darts than you were allowed to. But precision, so just be careful. It's a measure of repeatability. So you can be very precise but not accurate whatsoever. So just be careful when we talk about those things, okay? This is where it comes into significant digits. I'm not going to cover a lot of this. If you understand scientific notation and engineering notation, those are the biggies, and that's the main focus of these, all right? So I'm not going to break through all these. You can read through them. I'm not going to test you on those. The one I do need you to remember, though, is how to round numbers, right? If we're at 0.49, so let's say we have the number, I ask you to go to the nearest whole number and you have 1.49, you should know that rounds down to what? 1. All right, if I give you 1.50, that rounds up to 2. So notice that, 5 is the halfway point, right? Is where we round up or round down. Old school math that you should know how to do. All right, we got to go over some power rules from algebra just to review. All right, so that we know how we're handling all these engineering notations and things like that. If I give you some sort of power x to the n plus x to the n, x is the base. All right, in algebra, all right, the exponent doesn't change here. We just have 2 of that base. All right, so x to the n plus x to the n is 2x to the n. All right, let's try this. This is one you should know, right? X squared plus x squared is 2x squared. Notice the exponent doesn't change, but the value in front of the base does. And if we need to have numbers so that you understand it, right? We have 2 to the third plus 2 to the third. It's really what? 2 times 2 to the third. And if we break that down, it's 16. All right, let's look. What's the difference in this power rule? We're taking a base to an exponent times that same base to the exponent. Notice the key is the base is x in all of these, and the base is the same. So x to the n times x to the m means that we are going to take x and add the exponents. So when we multiply terms with like bases, we add the exponents. All right, so in this scenario, we're going to have x squared times x to the 4th. That's going to give us x to the 2 plus 4, which is x to the 6th. Okay, notice we're multiplying and not adding the bases in this case. We are adding the exponents. All right, let's do it with numbers. We have 3 squared times 3 to the 5th. That equals 3 to the 2 plus 5, which is 3 to the 7th, which is 2,187. Okay, those are some of the power rules. We're going to finish out the other ones. All right, if we have a base raised to a power all raised to a power, so we have x to the n to the power of m, we multiply those powers, so it becomes x to the n times m. Alright, so let's look at this. We have x cubed all raised to the 4th power, so it becomes x to the 3 times 4, which is x to the 12th. All right, make sure you're writing down all these rules as we go. It's okay to pause the video and write these down. All right, so if we have 2 squared all raised to the power of 3, we're going to get 2 to the 2 times 3, which is 2 to the 6th, which is 64. All right, so it all kind of breaks down. Let's say we have to divide, so we have x to the n divided by x to the n. Remember, the base has to be the same, and the base is x in this scenario. When we divide, we subtract powers. So x to the n minus m. Alright, so x to the 5th divided by x squared is x to the 5 minus 2, which is x cubed. This is very important when you start getting into logarithmic notation and writing things in terms of log and natural log. You're going to break everything down, using rules of exponents. Alright, let's look at this with numbers. Alright, say I have 2 to the 7th divided by 2 to the 4th. That becomes 2 to the 7 minus 4, which is 2 cubed, which is 8. Okay? So remember, the base has to be the same for all the power rules to apply. Why might we do this? Say I give you scientific, notation. You can plug this in your calculator, and it'll do the same, but maybe I don't let you use a calculator on a quiz. And you have to know how to make sure that these have the same power. So like right now, alright, that 10 to the 5th and 10 to the 6th don't have the same power. So I got to rewrite one of those numbers. So if we rewrite the 4 times 10 to the 6th, alright, this is being able to move and manipulate numbers. To write it in terms of 10 to the 5th, it's really 40 times 10 to the 5th. Alright, so we're going to move that around a little bit. Now, okay, I can take 40 and add it to the 3, and since they have the same base to the power now, it becomes 43 times 10 to the 5th. Alright, so because remember, we're adding these two numbers here. They're two scientific notation numbers, and we're adding them. So this becomes 3 plus 40, which is 43 times 10 to the 5th, because now they both have the same base. Alright, we're subtracting down here on the second example. I'm already giving you the answer. You got to decide, hey, am I going to take that 10 to the minus 13 and make it a negative 12, or am I going to take that 10 to the minus 12 and make it a negative 13? Let's take that 10 to the minus 12 and rewrite it so it's 10 to the minus 13. So now when I do this, becomes 45 minus 35, which is 10, and times 10 to the minus 13. Alright, say we're multiplying. So I'm just reusing the power rules here that we just learned about. Alright, adding and subtracting are the same, you just got to keep the same base. In this case, this one's fairly easy when they have the same base, right? So we add the exponents. So it's going to be 4 times 5, which is 20, okay? And then we're going to get times 10 to the 5th. Why 5th? Because 8, okay, plus negative 3 is 5. Okay, so that's why it's 20 times 10 to the 5th. So 4 times 5 is 20, and then the base, it's 10 to the 8 plus negative 3. 8 plus negative 3 is 5. All right, so let's look at this one. We're subtracting. All right, so it's 8 divided by 2, which is 4. Then we handle the bases, so it's 10 to the 9th divided by 10 to the 7th, so it's 10 to the 9 minus 7. So we get 4 times 10 squared, because 9 minus 7 is 2. Alright, moving forward here, we're going to talk about utility voltage and what a ground fault interrupt circuit is, or a GFI circuit. Alright, first of all, you see these outlets all over the place in your house, right? Most of the stuff in our lab is wired for 120. Now we have stuff in motor controls where we're wiring up and we're using 3-phase, 40 volts, a little bit more kick on that stuff. The big Fanic in class here, that one uses 480 volts. It's not 120 like the little guys in the cars. Okay, but most of these, all right, these are what are used at your house. All right, if you do any wiring at your house when you get older, maybe some of you have already done some. All right, you can go to Home Depot and buy a 2-conductor 14 with a ground. All right, or you might buy a 3-conductor and have a red wire. But we can get into that later on and classify that wire is there. All right, but you have 3 wires. Okay, so hot is always black, and like I said, there can be red if you buy a 3-conductor instead of a 2-conductor. All right, but hot is black, white is neutral. Neutral is our return wire. Alright, so that's our return path for our circuit to flow. And then we have safety, which is green or ground. Now if you've done wiring in your house, alright, there's a picture of a guy holding an actual circuit from your house. Okay, the ground wire when you're doing wiring in your house is not green. it's going to be a solid copper wire. All right, as you can see in the picture there. So the black is the hot, the white's the neutral. All right, and it's common. Always do it that way. Okay. But if you buy a light or a fan, it might come with a green wire. Know that that's usually going to be what your ground's going to connect to. All right, so just know those sort of things. It does matter when you have those plugs at your house, okay, and you notice that one side's bigger than the other. That's so you know how to wire it up too. All right, which side gets the neutral, which one gets the hot. The larger prong is the neutral. The smaller prong is the hot, okay? That way we're making sure that electrons flow in the right direction. That's why we do those. It matters for heavier equipment. So like, you know, there's some things that you can plug in that are only 2 prongs. Those really don't matter. But if you have something, you know, like your blender or your vacuum or those sort of things, those are going to matter. Okay, your heavy duty drills, things that require more amperage are going to do that, okay? And obviously the funky looking shape is left over. That's the ground. So make sure that you know that on a test, okay? Which one's neutral? Neutral's the big one, okay? And then hot's the little one. And then the funky round one is where your ground goes. Alright, so this one you might see where in your house. If any of you said like your bathroom or around a sink or outside, absolutely correct. Alright, these are the GFI circuits, or ground fault interrupt circuit. Okay, you're always going to see these around water. These are set to trip and protect everything on the circuit. So these kind of go above and beyond the circuit breaker in your house. It's more for safety. So that's why it's usually around water. So that the second that it detects that and there's a surge, this trips so you don't die and electrocute yourself. But all of your outside circuits. So if you lose power, like maybe in your garage or your outside circuits, chances are the breaker didn't trip. Something happened to your GFI, and you have to go reset the GFI and not the circuit breaker in your panel. So same you know, in your bathroom. So it's usually the first circuit in the series, and there'll be, you know, 3 or 4 more plugins that are on that. So, you know, your garage door might be on that. Your garage door might not be going up and down because the GFI that it's on got tripped. So you need to go reset it. Hit the red button there. It'll reset it. Alright. Usually there's a color indicator on each one of these. There'll be a red light if it's tripped, a green light if it's working. Alright. But you can see these different ones around your house. It's more for safety. And we always put it around water so that the second it hits, that water's not just live electricity and can kill you like you see in the movies and stuff like that. Alright, so the GFI, they're really just sensing, you know, a huge difference in between the hot and neutral. So like say something did get wet or things like that, it would trip. Alright, safety, we've talked about this already, but just going over things in here, okay, real quick. You know, because we're going to get into labs and going to be touching stuff that's going to be hot, and I don't want you getting shocked and things like that. So it's everybody's responsibility. Make sure we're all, you know, working alone. Don't do that in the real world. I mean, yeah, you might work at home in your house, but don't work when you're tired or things like that. Always try to work with someone. You know, if something does happen, especially with electricity, when you get shocked, it makes you clench your muscles, and sometimes you can't let go. You need someone to kill the power. But whenever you're working with electricity, you should always shut the power off anyways, okay? Don't wear anything that conducts. Don't wear your ring or tape it. Don't wear an electric watch. When you get into a heavy panel, like a 480 volt panel, like we have for our FANUC and things like that, okay, that stuff can arc to you. Don't ever stick a live screwdriver or things like that, alright? Make sure you know what's hazardous. Okay, make sure you're checking power cords, you know. They can get cut, melted, right? We talked about that in digital electronics when we were soldering. Some of you guys accidentally melted a power cord or things like that, okay? Don't ever touch energized circuits. Even the low voltage stuff, we'll work through that when we work on the 870 trainer and things like that as well. Maintain a clear workspace. So, you know, the biggest thing that bothers me is in the mechanical class, you know, we take off the shields to work and build the motors and gear drives and belt drives, and everybody sets the shields right where you trip over them and in your space. remove them, you know, get them out of the way. Make sure your tools aren't there where you're tripping on them. Make sure we always know, and I'll point out in class, where the main power is going to be shut off and the fire extinguishers. Okay? Absolutely, this is a no-no. Do not have foods or drinks anywhere we are working. I mean, preferably we don't really need them in class anyways, and nothing with an open container. Alright? Everything has to have a lid, even if you have water, things like that, please. Okay? Follow all lockout tagouts. I'll tell you when we need to use them and which labs they're going to apply to. Do that sort of thing. Alright, so on the quiz, okay, make sure you've gone through everything in the notes. You have a lecture quiz, alright, on this, making sure that I know that you went through the lecture. You have homework, alright, that's going to be due as well. And then we have our 4 major quizzes, the stuff that's on the major quizzes. You need to know all these different key terms, okay? They are all in your book at the end of the chapter, but you need to understand all the terms and definitions. And I'll go through them here, and you can pause the video, alright, and write them down. That way you know them. But they will be on all your tests and quizzes and things like that. I expect you to know these. You know, as you work with them, you'll get to know them. Do you have to know them word for word? No. But you should be able to pull them out of a multiple choice or matching type scenario. Alright, so key terms. You need to know all of these in here. Alright, know all of these as well. Like I said, pause the video if you need them. Alright, we're not going to go through this. I won't go through all of them, but it says a number written as 2.59 times 10 to the 7th is said to be what? There can only be one of these, right? Why is that? Because look at the exponent. Can that be an engineering notation? Is 7 a multiple of 3? It is not. So we know that that number is what? Only in scientific notation. Alright, so make sure when you're done with this that you guys do the lecture quiz. That'll be posted on my website. Alright, as well as, you know, make sure that you're doing your homework. I'll tell you when the due date is. And else, I will see everybody, and we will be ready to do our first lab.